is it 7th or 8th presentation, but last, Paul is going to be talking about Siderian Snowball Earth.
Yeah, so thanks for giving me the chance to say a few words about evidence for Paleoproterozoic low latitude glaciation and its possible relationship to the Great Oxidation Event. This stemmed from an attempt I made to consider a new correlation for Paleoproterozoic glaciations globally using the Great Oxidation Event itself as indicated by the disappearance of large magnitude mass independent sulfur isotope fractionation in sulfide and sulfate minerals as the basis for correlation. And my ideas on this were published in Chemical Geology in the De Holland volume, I think a couple of years ago now, so most of this has been published, although I will be able to update it with some as yet unpublished geochronological data from the Ulf Sunderlund lab in Sweden. So this is a log scale of oxygen concentration relative to the present, and this is the Great Oxidation Event as named by De Holland. And this is the familiar depiction now of ice ages over time. And so the question I'd like to address is the possibility that one of these Paleoproterozoic glaciations, one or more, may have been Snowball event or events, and whether or not it had any temporal or causal connection to the Great Oxidation. Now, I want to emphasize at the start that the Paleoproterozoic glacial record is rather anemic relative to the Neoproterozoic. In contrast to the Neoproterozoic, where there are over 100 formations described from 23 different paleocontinents, here we have only 13 formations on 7 cratons. That's the entire extent of the Paleoproterozoic glacial record. And only in North America and Southern Africa are there multiple discrete glaciations in one area. So there are other areas like Western Australia and Baltica, Arctic Canada, where there is a glacial record, but there's only one glacial unit. In North America, both in Ontario, Canada, and Wyoming in the United States, there are 3 discrete glacial formations. And in Southern Africa, there are at least 2. I will argue that there were 3 there as well. I'd like to begin with this remarkable series of lectures that were delivered in Belgium in 1856 by a chemist named Kuhne on the observed geological history of air. And what Kuhne noted was that there's a lot of organic matter in sedimentary rocks in the form of coal and tar, and the progressive burial of organic matter in sediment implies that the earlier atmosphere had less oxygen and more CO2 than the present atmosphere. Okay. Unfortunately, a lot of these slides are getting cut out, so I'll try to remember what is there. So this is oxygenic photosynthesis, and his point was that because of the burial of organic matter, the early atmosphere must have had less oxygen and more CO2 than the present one is, in effect driving that reaction backwards as you go backwards in time. And I mention this to make the important point that oxygenation of the atmosphere results from organic burial, not from photosynthesis, because photosynthesis and respiration are almost exactly in balance. So it's only the net burial of organic matter that releases oxygen to the atmosphere by effectively burying electrons. Now in the 1960s, the idea arose that the early geological record was deposited at a time when there was little or no oxygen in the atmosphere at all, and that oxygen rose rather abruptly near the beginning of the Proterozoic. Is there any way that the screen can be adjusted to
Maybe.
See, what's happening is that the top here is somehow, for some reason, showing at the bottom of the screen.
Mm. Any ideas, anybody?
Anyway, those four people came from rather different backgrounds. Lloyd Berkner was an atmospheric scientist who specialized in the upper atmosphere. Preston Cobb, that's better. Yeah, great. Preston Cobb is a geobiologist with USGS for many years, and then finally at UC Santa Barbara. Stu Roscoe is an economic geologist at the Geological Survey of Canada in Ottawa, and Dick Holland is a low-temperature geochemist at Princeton and Harvard. It was my good fortune to be colleagues with these three. I never knew Lloyd Berkner. Noted of these sort of four classic papers, the oldest one is by the youngest of these four, Dick Holland. And each of these people had somewhat different reasons for proposing that oxygen had risen abruptly at the beginning of the Proterozoic in what Dick Holland called the Great Oxidation Event. And I'll quickly review some of those reasons. If the light wasn't on it, this would look red. So this is it. Yeah, if you can turn down the front lights without turning, yeah, but then I can't see anybody. Yeah. Okay, so you can see it's red, so you can turn it back on. Okay. So the first appearance of red beds in the early Proterozoic was one evidence that was pointed to, indicating a rise of oxygen at that time. Here's another more powerful line of evidence from detrital minerals that are unstable in the presence of oxygen: uraninite, pyrite, siderite. You can see that is an abraded detrital grain. The presence of iron formations, which you're all familiar with. This is from the Hammersleys. And finally, geochemical evidence showing that there was a change from iron depletion in paleosols to iron enrichment in paleosols. Due to the fact that under anoxic conditions, iron is soluble, and under oxygenated conditions, it is insoluble. So this is a nice soil profile from Brazil showing strong iron enrichment in a paleosol developed on some basaltic volcanic rocks. Now, a major change took place in achieving a greater degree of temporal resolution and also quantification of the rise of oxygen as a result of the application of mass-independent sulfur isotope fractionation by James Farquhar and Huiming Bao, working in Mark Tiemann's lab in San Diego, California. And this exploited the fact that there are four stable isotopes of sulfur, and that although most chemical reactions result in mass-dependent fractionation, so this is a plot of the delta S33, that's 33S versus ratio over 32S, plotted against delta S34, falls on a mass-dependent fractionation line, which has a slope of very nearly exactly 0.5, 1/2. What is observed is that Archean sulfur-bearing minerals, sulfides and sulfates, plot off this mass-dependent fractionation line. In other words, they reflect mass-independent fractionation, with sulfides being enriched in 33S relative to mass-dependent fractionation, and sulfates depleted. And the mass-dependent fractionation is observed in all sulfide-bearing minerals that are younger than about 2 billion years old, but before, in the Archean, you see this mass-independent fractionation. And it's believed that the mass-independent fractionation results from stratospheric photochemistry, as a result of which the two major species that are emitted from volcanoes, H2S and sulfate, are driven towards a more oxidized and a more reduced end member, sulfate aerosol and elemental sulfur aerosol. And the sulfate aerosol, as a result of these photochemically induced reactions, is depleted in 33s relative to mass-dependent fractionation, and the sulfur, the reduced form, is enriched. And because the atmosphere is well mixed, and because in an anoxic atmosphere, the residence time of sulfur species in the atmosphere is low, these species are rapidly brought to the surface and incorporated in sulfate and sulfide minerals, resulting in a distribution of capital delta S33. So this is the deviation from mass-dependent fractionation, either an excess or a deficiency in S33, showing large mass-independent fractionations before about 2.4 billion years ago, and then no such large mass-independent fractionations after that time. And by large, I mean more or less than about 0.3 per mil. So this forms a very reliable basis for recognizing the rise in atmospheric oxygen above about 100,000th relative to the present level, 10 to the minus 5 relative to the present level. And the only thing that one has to be careful about in looking for these anomalies is to make sure that you are measuring the isotopes in primary or early diagenetic phases and not in detrital pyrite. So you must use framboidal pyrite that grows in the sediment, because detrital grains can carry that mass-independent signature into younger rocks. Okay, so the problem I sought to address is to use the disappearance of the myth, the mass-independent fractionation, as a basis for correlation of these glacial deposits. That was the exercise that I undertook, and as a result of which came up with a different global correlation, which, if true, would actually rationalize the record and bring the only known low-latitude glaciation of the Paleoproterozoic, the Machinini, one of the two here in the western part of South Africa, into coincidence with the Great Oxidation Event. Okay, so I want to look now at the stratigraphic records in these two areas, in North America and South Africa, and I'll use the Huronian supergroup on the southern margin of the Superior Province, which is formation by formation indistinguishable from the Snowy Pass supergroup in the south margin of the Wyoming Province. Most people think that the Wyoming Province was originally an extension of the Superior Province, but then drifted away and came back again. It's now thought in Geon 17, actually the latest arrival of the 6 major Archean cratons of interior Laurentia. So first, the Huronian. Glacial deposits have been well known since early in the 20th century in the Huronian. There are, in fact, 3 glacial units there. There are dimictites, there's isoraptic dropstones, extrabasinal clasts. And this is the Huronian stratigraphy in an idealized cross-section from south to north, 250 kilometer length scale. This is a rift and then passive margin subsidence-dominated basin. All the clastic sediment is coming off the Archean craton to the north. There's nothing coming from the south in the Huronian, so it looks like a rifted passive margin succession. The rift volcanics are dated about 2450 MA. The entire sequence is intruded by the Nipissing diabase at around 2220. There is one unpublished tough age high in the sequence at around 2.3. The brown are the 3 glacial units. The oldest one is called the Ramsey Lake, the middle one is the Bruce, and the youngest and most extensive one, and also the thickest, is the Galganda Formation. All of the other units are clastic sediments, except for the volcanics, and a single carbonate unit, which forms a cap carbonate on the middle of the 3 glacial units. That's the Espanola limestone. This is the same diagram, but now showing the evidence from the mass-independent isotope fractionation. So the paleosols are these half circles, detrital grains are this symbol, and these are the pyrites in framboidal pyrite in sediment, And the solid symbols represent anoxic conditions, that is, large fractionations, and the open symbols represent only very tiny fractionations. With the exception of this, the trinal minerals, that indicates also equivalent large fractionations, anoxic conditions. And as you can see, if you take this record on face value, it would appear that the change from very low concentrations of oxygen to significantly higher concentrations of oxygen is coincident with the middle of the three glacial units, the Bruce, the one with the carbonate. And there is additional evidence for a oxygenation event at that time in a thin siltstone layer that lies above the Bruce diamictite and below the cap carbonate. And this siltstone layer shows a large increase in radiogenic osmium and also in molybdenum, consistent with the rise of oxygen at that time. Okay. Any questions on the Canadian record? 3 glaciations. The middle one has a cap carbonate and seems to coincide, given the rather loose data constraints, with the Great Oxidation Event. Okay. Now, in South Africa, the key succession, broadly equivalent to the Huronian, is the Transvaal supergroup. And it's exposed in 2 areas, in the eastern Transvaal and to the west in the area known as the Griqualand West. These 2 areas of preservation are separated by an arch, the Freeburg Arch, where the older Ventersdorp volcanics around 2.7 are exposed. And so there are long-standing uncertainties about the correlation of formations within the Transvaal supergroup between these 2 areas, the eastern Transvaal and the Griqualand West area. This is a stratigraphic cross-section modified from Dave Evans of the Transvaal supergroup. So here's the Freeburg Arch, Griqualand West, eastern Transvaal, Ventersdorp volcanics underneath. In the lower part of the succession, there's a thick carbonate platform, the Kumbelrand platform, which goes into a basinal sequence to the west. These purple colors here are iron formations. There's a series of unconformities. And then there is a volcanic assemblage, which is terrestrial volcanics in the east, the Hekport Formation, and subaqueous volcanics in the west, the Onchuluk. And it's a pillow basalt hyaloclastite, quite different in facies from the Hekport, although traditional correlations due principally to Nick Bucas, a very experienced and outstanding sedimentologist, have always tended to correlate these 3. And then there's a clastic sequence on top, the Pretoria group, or the Olifantshoek subgroup in the west. Now, as you can see, there are a number of disconformities here. There's a major one here, and there are 3 here, and it's not exactly clear how these 3 feed into here, because after all, there's this gap here in the Freeburg Arch. It actually subcrops in Botswana, and so there is subsurface information, but no surface exposures. Now, as far as the glacial record is concerned, in both of these areas, Griqualand West and Eastern Transvaal, there are 2 glacial sequences. And it's usually been considered that they are correlative, although I'm going to question that. In Transvaal, there's 1 glacial unit here at the base of the Duitsland Formation, and then there's another one that's right underneath the Hekport volcanics. It's called the Boschhoek. Over here, there are also 2. There's one that's directly underneath the Onchuluk, and that's the Makanini, and this is the one that has paleomag, showing low paleolatitude. And then there's a little known one underneath here, the Doradale, which Nick Bucas has a student working on currently, and he tells me that this is actually a real glacial deposit. Now, once again, I've given the same symbols for the relating to the mass-independent sulfur isotope fractionation. And so from framboidal pyrite, it is known from excellent work by Guo, I think I'll show you a slide in a moment, that the Great Oxidation Event, the disappearance of the myth, is associated with a sequence boundary in the middle Duitsland Formation. In other words, it's younger than the older of the 2 glaciations, and older than the younger of the two glaciations. So the Great Oxidation Event seems to fall between the older and younger glaciation. And over here, the constraints are looser, but of this younger glaciation, you have anoxia in rocks that are older and oxid conditions in rocks that are higher. Now, this is a summary of Dave Evans' paleomagnetic data for the Macchianini. Actually, I should correct myself. The paleomagnetic data is not on the glacial deposits themselves, but rather on the overlying volcanics, on the Untitled. But the Untitled volcanics and the diamictite are intertoned. And this is seen very clearly in core, and there's lots of volcanic debris in the glacial diamics. So I think that Nick Bucas is on solid grounds on saying that the Macchianini glaciation and the Untitled volcanism are at least partly contemporaneous, and therefore that the paleopole for the Untitled volcanics can be applied to the glaciation. And this is Dave Evans' paleomagnetic data. There is an overprint and an older remnant magnetization, which has a positive, in fact, a double positive breccia test, in which you can see a random orientation of this likely primary pole and consistent orientation of the overprint. The poles fall here in Ecuador and yield a paleo latitude estimate of 11 plus or minus 5 degrees. So very low latitude implied for the Macchianini glaciation. And in fact, this is the only paleoproterozoic glaciation for which there are robust paleomagnetic estimates of paleo latitude. This is a summary of the dates. So the critical dates are that there are detrital zircon ages in sandstones associated with the Heckport lavas that are as young as 2225. That's actually a TIMS date on a detrital zircon. And there are a number of shrimp ages in the 2250 range. So accordingly, the Boschhoek diamictite has been considered to be younger than 2300, somewhere between 2300 and perhaps as young as 2220. And as Nick Bucas has always correlated the Boschhoek with the Macchianini, the low latitude ones, because they occupy analogous positions with respect to the overlying volcanics, Nick Bucas has always considered the Macchianini glaciation to have occurred in the 2200s, 2220, 2250, something on that order. In contrast, an economic geologist at Rhodes University named John Mohr, who died about 3 or 4 years ago, beginning early in the present century, I think around 2001, 2002, proposed that the Archelook was actually much older than the Heckport. It was not correlative, and I think part of his reasoning was the presence of a major iron manganese formation immediately overlying the Archelook. This is the hot as hell formation, and I think he thought that this was more comfortable down here than up here in these oxygenated clastic sediments. And he long pushed for a very different correlation from that of Nick Bucas. And when I thought about trying to use the MIF record as a basis for the correlation, I quickly became attracted to John Mohr's correlation. And the reason is that if you accept Nick Bucas's correlation, where the Boschhoek is, and the Macchianini is up here around 2.2 billion years ago, then there are rhenium-osmium ages for units at the top of the Deutschland formation, which would imply that the Great Oxidation Event shown, or the MIF disappearance shown by these red stars here, should be around 2.3 billion years ago. Whereas in North America, it's most likely that this middle glaciation is around 2.4. And this has just been stacked here, assuming a linear sedimentation rate. And because this is a passive margin sequence, this part of it here, it's likely that the sedimentation rate decreased exponentially with time, So these older units should be pushed to an older age. So I would think it's most likely that this middle glaciation and the Great Oxidation Event in North America is more like 2.4, or maybe even a bit older than 2.4, whereas in South Africa, it would seem it must be about 2.3. And in fact, if you look at the respective literatures, in South Africa, they always say the GOE is 2.3, and in North America, we always say it's 2.4. And that reflects the problems that arise with this correlation. Now, it's highly unlikely that the Great Oxidation Event is of a different age, you know, in different parts of the world, because the atmosphere is, is well mixed on the length scale of a few years. So that presents a problem. So, yeah, so that's not a problem with the slide. Maybe it's the number of slides I've used or something. Because there should be nothing wrong with that slide. So I can tell you what it says, and maybe I don't know whether we can get back to that. That was simply the Guo et al. Data showing the basis for the Great Oxidation Event in the Middle Deutschland Formation. It will show the mass-independent, the mass-dependent sulfur isotope fractionation, carbon isotope fractionation, and where are we? Yeah, it's back. Oh, wait a minute. It's this one. Yeah. Yeah, let's see. Yeah, okay, good. So this is the Deutschland formation in eastern Transvaal. This is the older diamictite. This is the younger diamictite. This is the mass-independent isotope fractionation, large magnitude. That's about 1 per mil. Disappearing to very small magnitude. There's also an increase in the mass-dependent sulfur isotope fractionation and in carbon isotope fractionation. The authors said the transition occurs in this interval. I've chosen to consider that oxidation actually coincides with this sequence boundary. And what I'm going to suggest is that this sequence boundary is the surface of the Macchianini glaciation. And there just don't happen to be any glacial deposits there, or they haven't been recognized. And this is not a problem. You know, I spent 25 years working in the Canadian Shield in areas where the Precambrian was extremely well exposed. In other words, there are no damn Pleistocene rocks or sediments, despite the fact that the Canadian Shield has been underneath the Laurentide ice sheet for the vast majority of the last 2.5 million years. So ice sheets tend to move material out to their periphery. That's why the Laurentide ice sheet took all the soil off Canada and put it in the United States. And leaving Canada. This is why Canadians and Americans are quite a bit different, politically and sociologically. Canadians are more like prospectors, and Americans are more like farmers. And it's because of the Laurentide ice sheet. And prospectors are people that always hope for the best and seldom find it. And it's Canadians, aside from self-righteousness, that's the only gold medal event. Americans are more like farmers. Farmers fear for the worst and find it everywhere. Laurentide ice sheet. Anyway, so my thinking was that this is actually the Macchianini glacial surface here, and it's a sequence boundary. Maybe there is evidence of glaciation. Someone should look for it. Now, if you do that, then you've got 3 glaciations. Okay, an older one, a middle one, and the youngest one, and this is the one that's associated with the Great Oxidation. Right? Sounds like North America. So if you look at it that way, so here's Eastern Transvaal, here's Griekenland West, there's the Great Oxidation Event, that's the sequence boundary. This is plotted against time rather than stratigraphy. So here you have 3 glaciations, middle one corresponding to the Great Oxidation. Here's the middle one here. You don't have an equivalent of the Boschhoek over here, but you have an equivalent of the lower Deutschland. That's this one here, the Doradale. Okay? And in that way, you can make the Great Oxidation about 2.4 billion or so. and have 3 glaciations in South Africa, just like you have in North America. And so here's Ontario, here's Wyoming. The middle one with the cap carbonate, I would make that the Machinini. The red are where you have no myth, and the green is where you do have myth. And everything becomes very simple, and you have the low latitude glaciation corresponding to the Great Oxidation Event. And of course, there are a lot of reasons for thinking that that's sensible. Atmospheric people would expect that a rise of oxygen would actually cause a major glaciation, because you would be removing all the reduced greenhouse gases like methane or SO2. There are a number of reduced gaseous species that have strong greenhouse properties, and if you raise oxygen, you get rid of them. And if you raise oxygen rapidly relative to silicate weather and feedback, then you would cause a major cooling. I tend to look at it the other way around. I like Snowball Earth as a way of actually raising the oxygen, rather than raising the oxygen for some mysterious reason and causing the glaciation. There could be a feedback, of course. And that actually even works pretty well with the existing dates. So these are the available dates directly. These are dates of sedimentation. And this is the correlation that I propose. The black and yellow symbols are the myth and no myth. And this is the gradient oxidation and the low latitude glaciation, and these are the available dates. Now this was as the figure that was in the chemical geology paper. Since that time, there has been, was presented at the AGU, Geological Association of Canada joint meeting in Montreal last spring, 7 new dates from badleite, uranium-lead badleite, from subvolcanic sills that are presumably or believed to be associated with the Ongelup volcanics. And in fact, one of them, the Westfold sill, has the same pole as the Ongelup volcanics. And those ages are in this ballpark here of 2420. And if that's really correct, that 2420 is the age of the Ongelup volcanics, then the correlation first proposed by John Mohr and supported by myself actually looks pretty good. I do, however, have to mention that Nick Bucas reported detroidal zircons in the Machinini as young as 2250 in an abstract at Geological Society of America meeting 3 years ago. And of course that would be inconsistent with the correlation I proposed. Those data have not yet been published, although he is going to present more data at the upcoming IGC in Cape Town. I looked at his poster very carefully in Denver. He had 13 grains, so it's not just a lone contaminant. Richard Armstrong also did detrital zircon dating in the Machinini and found no young grains. He found no grains younger than 24 or 40, as I recall. So I don't know, at this point, I honestly don't know how this is going to pan out. We have conflicting geochronological evidence as it stands right now. I won't be at the meeting in IGC in Cape Town. If any of you are going there, have a look at, well, I guess Nick's will probably be, Nick Bucas will be an oral presentation, so I'll be keen to, and tell him that it needs to get published. Because this is an important issue, I think, that should be resolved. I know Nick's a busy man, and he's an honorable person and a superb geologist, but that data needs to come out. Okay, so that's my thinking about possible connections between a Paleoproterozoic snowball earth and the Great Oxidation Event. So that's my story.
Any questions?
Yeah, Chris.
Yeah, the question about the Huronian. So the Espinola Formation, which is the cap carbonate sitting on top of the Bruce,
Yeah.
as I recall, has very negative delta 13 values.
Yeah.
And so the carbon isotopes wouldn't match up with the Greek one, which is much higher in the delta 13. Is there any reason why I guess you would explain, or how you would explain the the discrepancy between the carbon isotopes.
Well, the isotopes, I'm not sure what carbon isotopes you're referring to from Mohr.
No, from Huingbao's paper. So if you had the slide in just a little while ago from the Deutschland. So right there.
Oh,
on
these.
Yeah. So the Espinola has values between like -1 and -4.
Yeah, but so that's in the cap carbonate.
Right.
That directly follows on the dimictite. This is some uncertain interval later.
Right.
So, for example, in Namibia, in the cryogenian cap carbonates, they begin negative, but then they go positive. Quite quickly in time. So there is no carbon isotope record right in here where you would really need it. Yeah.
Yeah, so I was in the field with Nick a few years ago.
Yeah.
We were driving past the Onkalok, and he said, "Oh, there's no good age for these."
Sorry, which?
The Onkalok lavas.
Oh, look, yeah.
Yeah, so we were driving, he said, "There's no good age for these." So we collected a sample,
Yeah.
and I dated it using a SM&D isochron. And it's 2351 from the SM&D isochron. So more consistent with those Badleyite agents.
Yeah, it's kind of intermediate. 2361?
2351, 2358, but plus or minus 68. So it's got a pretty large error bar on it.
Yeah, right.
But it's not. So I agree. I think it's older.
Yeah,
I agree with you.
So then if I can ask a question.
If that's a whole rock isotope,
It's a whole rock and mineral isochron.
whole rock and mineral.
Yeah.
Yeah, because a whole rock isochron on a highly altered basalt. So the Onkalok, as there's an old rubidium strontium 2220 was one of them. Anyway, so yeah, those are altered rocks. So I wouldn't trust a whole rock.
Well, the SM&D will be relatively robust. But the critical thing, look, I agree with you. That's what I'm saying. With the data that I have, and the data that you showed, say the same thing.
Yeah, that it's older than the Heckborn.
Absolutely.
Do you have a Sumerian neodymium age on the Heckborn?
No, that I don't have. I've talked to Nick about doing that.
Let's talk about this more. I never understood actually what the significance of a Sumerian neodymium isochron on the basalt is.
Sure.
At least in
Sure.
terms of crystallization.
Sure. And I've seen Nick sent me his tetralzircon data.
Yeah.
And those young ages, they're pretty uranium rich, zircons. And so they're likely metavention some
Experience early
age.
lead loss.
Yeah, I don't think those are primary age. I don't think those are real ages. I think they're older. I talked to Martin Van Kranendonk, who's looked at trial zircons in here from the sandstones. The youngest one he gets is 24. No problem. Those ages are spurious that Nick has. I've told him. I'm going to see him in like 3 days. So I'm going to talk to him about it again.
Okay, yeah, well, that's obviously the most likely culprit is early lead loss.
Absolutely.
And if they're uranium rich.
So I agree. I think those lavas are older. I agree with you.
Chris?
I was going to say that, there's a lot of contradictory lead isochrons from the Onkalok, which is 2022, or 222, and then there's another lead isochron from some of the overlying carbonates that is like 2390. So, I don't know, I guess then I would argue
The
that
lead stuff is an overprint from the Bushveld.
Sure, I can accept that, but then I would argue that your large uncertainty implies that your MSWD is quite high, which then calls into question whether or not you're seeing a single population on your isochron.
Sure. The MSWD is small. I'll look it up. I'll tell you what it is, but it's pretty small. I mean, the error bar is large, 68, but it doesn't get you down to 2222. Absolutely not. And the Badleyite ages are absolutely consistent.
Yeah, I think that the high uranium in the tetralzircons is probably more likely to give you spurious ages. But,
Sure.
But I would be very hesitant to hang my hat on a whole rock SM&D isochron, especially with an uncertainty that large.
Sure. I'm just saying it doesn't disagree with the older ages that are published. That's all I'm saying.
An uncertainty that large doesn't necessarily mean the MSWD is high. It just depends on the amount of spread you've got on the isochron.
Sure. It depends
It
on.
can be a good age, but not a very precise one.
Sure.
Yeah.
Sure.
Any other questions?
Paul, the badly ages from Ulflab, those are all Ivy Tim's ages?
I believe so, yeah. But once again, they haven't been published either, so I don't know the details. I think they've been submitted, but I haven't seen the paper. One of them has, the Vestfold Sill has been, but there are 6 others that were presented in Montreal. I've heard they've been submitted, but I haven't seen them actually. What's the latest on meteorite Mohr?
Cranendonk has some stuff going on right now, but he's kind of dragging his heels. So we'll see if Mark has anything to say.
Okay, so thanks once again, Paul.